Okay, today's lecture. Let's discuss about the question and answers of inorganic and physical chemistry. Let's go to the first question. What are isothermal and adiabatic process? A process is said to be isothermal if the temperature of the system remains constant during each stage of the process is called isothermal process. A process is said to be adiabatic if no heat enters or leaves the system during any step of the process. In the adiabatic process, heat Q is equal to 0. Let's go to the next question. Give a reason even at 0 Kelvin, the temperature, the entropy of the crystalline carbon monoxide is not 0. The third law of thermodynamics states that entropy of a perfectly crystalline substance, at absolute 0 is 0. However, crystalline carbon monoxide is not a perfectly crystalline substance. It contains defects such as vacancies and interstitial atoms, which give it a non-zero entropy even at 0 Kelvin. The residual entropy of CO molecule is 3.4 joules per Kelvin per mole at 0 Kelvin. This implies that CO molecule does not have a perfect arrangement of CO molecule. We can say that in the crystalline state, its arrangement like CO, CO, CO and OC, CO, CO and OC may not have a significant energy difference. That is, CO has more than one arrangement possible at 0 Kelvin. That is, the number of microstates is more than 1. So, entropy is not 0. So, with this, we'll go to the next question. Give the statement of second law of thermodynamics. It is impossible for a cyclic process to take heat from cold reservoir and convert it into work without at the same time transferring heat from a hot to cold reservoir. It is impossible to construct a machine which is able to convey heat to cyclic process from one reservoir at a lower temperature to another at a higher temperature unless work is done on the machine by some outside agency. Entropy of the universe remains constant in a reversible process but increases in an irreversible or spontaneous process. But entropy of the universe never decreases. All naturally occurring processes always tend to change spontaneously in the direction which would lead to equilibrium. Let's go to the next question. Spontaneous process. Spontaneous processes are those occur naturally without any external intervention or input of energy. The process tend to proceed without any external agency under specific condition. The key characteristic of a spontaneous process is that they lead to decrease in overall Gibbs free energy. That is, delta G is reduces, means decreases of the system. If delta G is negative, the process is spontaneous. For example, ice melting at room temperature. When an ice is exposed to a temperature above its melting point, it naturally melts and transforms into liquid water. The process occurs spontaneously because it leads to decrease in Gibbs free energy. Second example, formation of the rust. When iron is exposed to oxygen and moisture, it gradually oxidizes and forms iron oxide. It's called rust. The powder, the brown color powder present in a steel is called rust. This process occurs spontaneously as it leads to a decrease in Gibbs free energy. Let's look into the non-spontaneous process. Non-spontaneous processes are those that do not occur naturally and require external intervention or input of energy to proceed. These processes have a positive delta G, means free energy, require additional energy to proceed reaction, indicating an increase in Gibbs free energy. Non-spontaneous process cannot occur without the addition of energy from an external source. For example, water boiling before its boiling point. Water normally boils at 100 degrees Celsius at standard pressure. However, if the temperature is below the boiling point, the water will not spontaneously boil. The process requires the addition of heat energy to increase the temperature and initiate boiling. Second example, charging a battery. The process of charging a battery involves the input of electrical energy to reverse the chemical reactions that occur during the discharge. Charging is a battery is a non-spontaneous process as it requires external energy to proceed against the natural direction of the cell reaction. Let's look into the two examples of extensive properties. Mass and volume are the extensive property. Density and the temperature are the two examples of intensive property. So with this, let's go to the next slide and let's take one more question. Explain the molecular interpretation of entropy. State third law of thermodynamics. The molecular interpretation of entropy connect the concepts of entropy to microscopic behavior and arrangements of molecule in a system. It provides insight into how the disorder or randomness of a system arises at the molecular level. Entropy can be related to the number of microstates available to a system. In this context, a microstate refers to a specific arrangement or configuration of the individual molecules or particles in a system. A microstate, on the other hand, represent a specific sets of microscopic properties of the system, such as temperature, pressure, and volume. As the system temperature increases, the kinetic energy of the molecules also increases, allowing them to explore a greater number of possible microstates. A higher number of microstates means more ways for the system to distribute its energy and particles among the different molecular arrangements. Consider a simple example of a gas in a container. At a low temperature, the gas molecules have a lower kinetic energy and are confined to fewer possible positions and velocities, resulting in a fewer microstates. As the temperature increases, the molecules gain more kinetic energy and can occupy a greater variety of positions and velocities, leading to a larger number of microstates. Entropy can be thought of a measure of the multiplicity of microstates that corresponds to a given macrostate. A microstate, a macrostate with a higher number of corresponding microstate has a higher entropy. A macrostate with a higher number of corresponding microstate has a higher entropy. Let's continue in the next slide. Okay, additionally, the molecular interpretation of energy is related to the concept of probability. Entropy is proportional to the logarithm of number of microstates, and this logarithmic relationship arises due to probabilistic nature of molecular behavior. The more microstates there are, the more equally probable the system is to be any one particular microstate. In summary, the molecular interpretation of entropy connects the macroscopic concept of entropy to the microscopic behavior of a molecule in a system. It involves the number of microstates available in the system, the distribution of molecular arrangement, and the probabilistic nature of molecular behavior. Understanding the molecular interpretation of entropy provides a deeper understanding of the relationship between the disorder, randomness, and behavior of the molecule in a system. Okay, with this, let's go to the next slide and we'll take one more question. Explain the calculation of absolute entropy in case of solids. What are the spontaneous and non-spontaneous reactions? Give example. Classify the following into extensive and intensive properties. Okay, let's take the first one, calculation of absolute entropy in case of solids. The calculation of absolute entropy in case of solid involves determining the entropy of a change from a reference state. The reference is state usually at 0 Kelvin to the desired temperature other than 0 Kelvin is called desired temperature. The absolute temperature of the solid depends on the factors such as number of ways the atoms or molecules in a solid can arrange themselves and vibrational motion of the particles. The calculation of the absolute entropy for a solid involves three main steps. First is establish a reference state. Since the entropy is a measure of disorder, it is convenient to establish a reference state at absolute zero temperature, that's called 0 Kelvin, where the solid is assumed to be perfectly ordered. Since the molecules present in a solid are perfectly ordered, then as a minimum or minimal vibrational motion. In this state, the entropy is taken to be zero. Consider the vibrational motion. At a non-zero temperature, means other than 0 Kelvin, the atoms or molecules in a solid vibrate about their equilibrium position. The vibrational motion contributes to the entropy of the solid. The quantization of vibrational energy level can be described by the principle of quantum mechanics. To calculate the vibrational contribution to entropy, one can use the Einstein or Debye model. The Einstein model assumes that all atoms in a solid vibrate at a same frequency. It's called Einstein frequency. That means Einstein model assumes that all atoms in a solid vibrate at a same frequency. It's called Einstein frequency and have the same energy. The Debye model considers the distribution of vibrational frequency within the solid. Let's continue in the next slide. In either model, the vibrational entropy can be calculated using the equation. This is R. Okay, where S is the vibration is the vibrational entropy. S is the means entropy of a vibration. It's called vibrational entropy. R is the gas constant, that is universal gas constant 8.314 joule per mole per Kelvin. And N is the number of vibrational degrees of freedom. And theta is the characteristic temperature of the model. Einstein or Debye temperature. T is the absolute temperature. Add a contributions from other factors. In addition to the vibrational motion, other factors such as electronic energy level, rotational motion for molecules, and any magnetic contributions may also contribute to the entropy of the solid. These contributions are typically small and may be neglected even in many cases. By summing up, the vibrational entropy and the other relevant contributions, the absolute entropy of the solid at a given temperature can be calculated. It's important to note that calculating absolute entropy of a solid can be complex and accurate. Predictions often require sophisticated quantum mechanical calculations. Okay, with this, I will take up one more question in the next slide. So, explain thermodynamic scale of temperature and give the two examples of the state function. Let's take the first one, explain the thermodynamic scale of temperature. The thermodynamic scale of temperature, also known as the Kelvin scale, is a temperature scale based on the laws of thermodynamics. It is named after the Scottish physicist William Thomas, first Baron Kelvin, who made a significant contributions to the field of thermodynamics. The Kelvin scale is an absolute temperature scale, which means that its 0 point called absolute zero corresponds to the complete absence of the thermal energy. In this scale, temperatures are measured in Kelvin. It is denoted by the symbol K units. The Kelvin scale is related to the Celsius scale by a simple linear transformations. The Kelvin value is equal to the Celsius value plus 273.15. For example, water freezes at 0 degrees Celsius, which corresponds to the 273.15 Kelvin, and water boils at 100 degrees Celsius, which corresponds to the 373.15 Kelvin. The Kelvin scale is widely used in specific and engineering applications, especially in thermodynamics and physics, because it has several advantages over the Celsius scale. Firstly, it is aligned with the absolute zero of temperature, making it suitable for calculations involving temperature difference and energy calculations. Secondly, it eliminates the need of negative temperature value, as there are no negative values on Kelvin scale. Finally, the Kelvin scale is considered with the ideal gas law and other thermodynamic equations. The two examples of the state functions are entropy, enthalpy, and internal energy are the examples of state functions. With this, let's take one more question. More particularly, derive Gibbs-Helmholtz equation. We know that the free energy change equation, that is G is equal to H minus Ts, and enthalpy of a reaction is H is equal to U plus PV. In this, G is the free energy, Gibbs free energy, H is the enthalpy, T is the temperature, S is the entropy, and hydrogen will be the enthalpy, and U will be the internal energy, P is the pressure, V is the volume. Differentiate free energy equation and enthalpy equation, you will get these two equations. Now we know that this is the dH. dH means nothing but a differentiated enthalpy. This value you can add in the Gibbs free energy differentiated one. Then you will get an equation 1. Then for the reversible reaction, heat of reversible is equal to T delta S. And from the first law of thermodynamics, internal energy is equal to heat of reversible plus work done in a reversible reaction. If work done is only a mechanical, then W is equal to minus PdV. Substituting this value means W is equal to P minus PdV, you can substitute in the equation 2. Then equation 2 become du minus Q means heat of reversible plus PdV, that is equal to 0. So you can find that in equation 1 du, okay, this is the one, and Q of reversible and PdV, okay, this one, and T delta S, okay, will be equal to the 0. Then equation 1 will become, we'll go to the next slide. Equation 1 will become dg is equal to VdP minus SdT. At constant pressure, dP is equal to 0. Then this VdP becomes 0. Then dg is equal to minus SdT. When you are taking dt into the left hand side, then dg by dt at constant pressure is nothing but a entropy. Then differentiate, then if you are writing change in free energy and entropy for initial state and the final state, these two are the equations. And this will be combined initial state and the final state free energy, initial state and the final state of the entropy. And when you are taking, when you are, you can change in entropy, we can write it delta G. Change in free energy, you can write it as delta G. Change in entropy, you can write it as delta S. Now we know the value of change in entropy. This value of change in entropy, we can add to the isothermal free energy change equation. Then we'll get a Gibbs-Helmholtz equation. Okay, these are the few important questions in thermodynamics. I will stop today at this stage and will continue in the next class.